Well, thanks for coming, everyone. Welcome back. In the last section, what I was talking about was one method for evaluating the performance of a clinical prediction rule. A very important measure, calibration, seeing if what the model predicts as an outcome for a person seems to reflect his true risk. And the way we did that is we divided people into subgroups which had roughly similar risks and saw for the group if the total number of observed outcomes, total number of deaths in the previous example, matched up with what was expected to happen. Well, there's another measure of performance we can talk about in addition to calibration that describes the performance of a prediction rule. It's called discrimination, and that's what I'd like to talk about now. Now, discrimination refers to the ability to separate people according to their outcomes, separate the people who end up dying from the people who did end up not dying based on what the predicted risks are. So basically what I'd like to be able to say is, let's suppose I have a prediction rule, like the mortality prediction rule. I apply it to a group of people, say the 2,000 people in the previous example, and I line people up against the wall by the value for their predicted risk. So in the top of the line is everybody who have the highest predicted risks, and the bottom of the line is everyone who has the lowest predicted risks. Then what I'd like to be able to say is, if I knew the actual true outcomes, I'd like to see if all the cases of death were at the top of the line and all the survivors are at the bottom of the line. If so, the predicted risk is separating people, separating the outcome classes of the people, the deceased people, the dead people from the non-dead people, according to their predicted risk. So discrimination refers to the ability to separate people in different outcome categories by looking at their predicted risks. So essentially lining people up against the wall and seeing if the people on the top of the line are the people who develop the outcomes and the people on the bottom of the lineup are the people who don't. Now, how do you quantify that? Well, first of all, you could describe that lineup by drawing something called an ROC curve. And Marcello's talked about ROC curves earlier in this class. And you can measure something called the area under that ROC curve as a single number to describe the discrimination ability of your prediction rule. Now, how you do that mechanically is the following. To build an ROC curve, you have to essentially take your lineup and divide it or collapse it into two groups, high-risk people versus low-risk people. So what I'll do is I'll line people up by their predicted risks, and I'll set a threshold, say 50%, as a threshold for separating high risk from low risk. So what that's doing, it's collapsing my lineup by people by predicted risk by some threshold to create two groups of people. High risk, meaning their predicted risks are bigger than 50%, and low risks, meaning their predicted risks are less than 50%. And I want to see if that high risk, low risk classification matches up with what actually happened to people, whether they did or did not develop the disease. So this is what you're going to end up with once you create that threshold to define high risk and low risk. You're going to have a certain number of people whose predicted risks are, say, bigger than 50%. They're going to be classified into the high risk group. And the low risk group is everyone whose predicted risk is less than 50%. You then can classify people as high risk or low risk, also look at their outcomes, whether they did or did not develop the outcome. You can build this 2x2 table. Well, this is the sort of table we had in the previous series of lectures when we talked about screening and trying to describe how well a screening test matches up with what actually happens to people. The screening test, remember, classified people as being likely or unlikely to have a disease in the preclinical state. The way we quantified the ability of the screening test to accurately, validly match up with what actually happened to people is we calculated things called sensitivity and specificity. Sensitivity was looking at everybody who actually had the disease, or in this case, has the outcome, and ask what proportion of those people are classified by the prediction rule using the threshold I chose as being high risk, A over A plus C. Specificity looks at people who don't have the outcome and looks at how many people proportionally wise are classified as low risk, D over D plus D. So once I choose a threshold, I can calculate a sensitivity and a specificity for that threshold. Now, this table is based on people being classified as high risk or low risk if their predicted risk from the prediction rule was bigger than 50%. Let's suppose I change the threshold from 50% to be 60%. So high risk now is anyone whose predicted risk is greater than or equal to 60%. And low risk is going to be anybody whose predicted risk is less than 60%. Now what's going to happen? Well, before, if your predicted risk was 55%, you were called high risk because 55% is bigger than 50%. But 55% is not bigger than 60%, so now you're going to be called low risk. So some of these people in the A group who before were called high risk because their risk was bigger than 50, some of them are no longer going to be high risk. They're going to be reclassified as being low risk. So there's going to be some movement of people in the A cell moving down to the C cell. A is going to get smaller. On the other hand, over here we had before people called low risk if their risk was less than 50%. Now low risk means if your predicted risk is less than 60%. So some of the people who are in the B cell are also going to be moving down into the D cell. So the D cell, the total number of people predicted to be at low risk, is going to get bigger. So what's going to happen in terms of sensitivities and specificities now with the 60% threshold versus before with the 50% threshold? Well, the A cell is going to get smaller, so the sensitivity is going to have the same denominator, A plus C people, but the A is going to get smaller. The sensitivity is going to go down with the change in threshold from 50% to 60%. But the D cell is going to get bigger. So the specificity is actually going to go up. So by changing the threshold, you get a different value for sensitivity and specificity of high risk versus low risk, depending on your threshold for what you're calling high risk. That allows you to draw what is called an ROC curve. It allows you to calculate a bunch of values for sensitivities and specificities for different points, and from those draw an ROC curve to describe the performance of this. So for example, if I go back to the mortality prediction model from the previous example, remember there were 1,997 people. It turned out that 396 of them actually died during the hospital stay and 1,601 didn't. If I choose a threshold of 50% for classifying a person as high risk or low risk, I'll get a sensitivity of 42% and a specificity of 95%. If I change the 50% threshold to be some other value like 60%, my sensitivity is going to go down, my specificity is going to go up. If I change it from 50% to 40%, the opposite will be true. My sensitivity will go up, my specificity will go down. It's a seesaw effect. Every threshold I pick, I'll get a value for sensitivity and specificity for that threshold. So what does an ROC curve do? It's going to plot a series of points in two-dimensional space. It's going to plot on the x-axis the value for 1 minus specificity for the 2x2 table we looked at before for a given threshold. So if your threshold was 50% on the previous table, your value for 1 minus specificity is going to equal 1 minus 0.95 or 0.05. That's going to be a value on the x-axis, the horizontal value in this two-dimensional space. The y-axis is going to be your sensitivity. So what an ROC curve is going to do is for every threshold you get a value for sensitivity and a value for specificity. That's going to give you a point in two-dimensional space, and you're going to be plotting on the x-axis the value for 1 minus specificity, and for the y-axis you're going to be plotting the value for the sensitivity. So you're going to get a series of points which you can connect with a curve. And basically, if you use the previous example, the mortality prediction rule, and chose different thresholds, your ROC curve would look something like this. It's this particular point, where every time the curve is bending, it's corresponding to a different threshold with a different point for sensitivity and specificity. Well, what's a good ROC curve? Well, a good ROC curve would mean it would have a point up near this top left-hand corner. If you're up near that top left-hand corner, your value for sensitivity is approximately 1. Your value for 1 minus specificity is approximately 0. That means your specificity has to be approximately 1.0. So if your ROC curve goes up to that, close to that left-hand top part of that box, you have a point, a threshold, separating people into high and low risk, that it has nearly 100% sensitivity and nearly 100% specificity. Great discrimination It's doing a great job predicting, separating those who got the disease from those who didn't get the disease or the outcome just by looking at whether they're classified as high risk or low risk. So what we can use to measure how close this curve comes to that ideal point is to look at the area under the curve. Now remember, this box can go no higher than 1.0. That's as high as the sensitivity can be. It can go no lower than 0. The x-axis, 1 minus specificity, can go no lower than 0, no higher than 1. So the entire box has a height of 1 unit and a width of 1 unit. The total area inside the box is 1 times 1. So we want the curve, the area under the curve, the AUC, to be as close as 1. If it is, we have good discrimination. So in this case, using the mortality prediction rule, it turns out that the area under the ROC curve is 0.85, which is pretty good. It's getting close to that value 1.0. So what we would conclude from this example is that this clinical prediction rule not only has good calibration, but it also has good discrimination because the area under the ROC curve, from the curve you drew, we're using different thresholds, separating people in that lineup, calling them high risk or low risk, does a pretty good job separating people who really did have the outcome, they died, from people who really didn't have the outcome, they didn't die. So this is the other way we epidemiologists measure the performance of a prediction rule, namely discrimination. So now that we have these measures, calibration and discrimination, to describe the performance of a prediction rule, how can we use them to validly describe how well our model would work in future people? And that's what I'd like to talk about in the next segment, is how we decide to use these measures to estimate how well they work, not in the data set from which they were created, but how they work in future people, which is the real goal of a clinical prediction rule. I'll see you then.